All right, so question number one asks us to write a simple function that multiply two numbers. So notice now we're going to start getting into using that if underscore underscore name equals underscore underscore, it's an extra underscore, underscore main, then do a certain function. And this is, again, just a little safer way to code your programs. You have a little bit more control over what runs or what doesn't run. And quite frankly, I think it looks a little bit prettier to do. So you can see here we just have our multiply function. We have two parameters, num1 and num2, multiply them together and print them out to the screen. So let's go ahead and try that. 1 multiplied by 2 is 2. Let's do 10 multiplied by 2. We should get 20. 10 multiplied by 20. It's going to give us 200. Okay, so question number 2 asks us to solve the Fibonacci sequence using a function. So if you're not familiar with the Fibonacci sequence, I'm going to link a resource in the description below that will walk through what the Fibonacci sequence is and how it works, and so on and so forth. To solve this program, since we're using a function, we're going to be introducing a concept called recursion. What recursion basically does is it uses a function to call itself to solve a problem. So this basic one, as you can see, is only about 4 or 5 lines. We define our Fibonacci function with our number that we're going to calculate the Fibonacci sequence for. We want to assert that that number is positive. We can't calculate the Fibonacci sequence with a negative number, or at least for our purposes, we're not going to. And then we're going to check to see if that number is either 0 or 1. If it's 0 or 1, those are the base cases of the Fibonacci sequence, the default cases, since you don't subtract anything from them. And so in our recursive function, we're going to call them our base cases, because they're going to be what tells us to stop doing this recursive function. So we're going to return 1. Now for the rest of them, we're just going to return the Fibonacci of num minus 1 plus the Fibonacci of num minus 2 and add those together and return that back out. So if we go ahead and we run it here, we're going to go ahead and run the Fibonacci sequence of 10. I'm going to comment these out. And if we run this, we get 89, which is the Fibonacci sequence. Now the problem with this function is that it grows at an exponential rate. What that basically means is as our number gets bigger and bigger and bigger, the time that it takes for us to calculate the Fibonacci sequence is also going to grow exponentially. So it's going to take us exponentially more time to calculate a number. So for instance, we can calculate the Fibonacci of 1 really fast. We know the Fibonacci of 1 is 1. We can even calculate the Fibonacci of 10 relatively fast, as you saw here when I ran 10. But if we try to calculate the Fibonacci of 95, notice that it's going to keep running and running and running and running and running because it takes so much work for it to calculate. And the reason that's the case is because it has to do Fibonacci of num minus 1, num minus 2, and then for each of those num minus 1, num minus 2, it has to calculate the Fibonacci. So if we were to type it out, so we have the Fibonacci of 95, but to get the Fibonacci of 95, we have to do the Fibonacci of 94 and 93. And to get the Fibonacci of 94, we have to do 93 and 92, and 92 and 91. And so you notice that we're doing a lot of repeat work here. We have to keep doing this. We have to go all the way until we get to like the 0 or 1, 0, 1, 0, 1, 0, 1, 0, 1, so on and so forth, right? But now, as you're seeing here, we're doing a lot of repeat work here. We're calculating the Fibonacci of 93 2 times. We're calculating the Fibonacci of 92 2 times, and so on and so forth. And so we want to come up with a way to reduce that extra work that we're doing so that as our size of our Fibonacci increases, we're able to solve it in the same amount of time, in a linear time span. And so that's where this Fibonacci advanced sequence comes in. And so if you're, this is again more advanced. If you find this a little confusing, don't worry about it. As you get some more practice, it'll make a little bit more sense. But the idea with this advanced Fibonacci is that instead of, if we go back to our example here, instead of redoing this, we're going to just save this value, this 93 Fibonacci sequence, whenever we calculate it, and then simply just use it whenever we see it again. So whenever we see 93 pop up, we're like, oh, it's in our list of values. We're just going to simply go ahead and use it again. And so that's what this dictionary of past num is doing, is it's holding those previous Fibonacci values in a dictionary. Once again, we're going to assert that our value is greater than -1. We're going to check to see if we're less than 2, because that's going to tell us to stop doing this recursive stuff. We're not going to, once we get to 0 or 1, we're going to not have to calculate any more Fibonacci sequences after that. We know the Fibonacci of 0 and 1 are always going to be 1. Now here's where we get a little different. We have this if, we have these lines of code here for each of them. So we're going to create a variable called 1 less, which is going to hold the value of 1 less of the Fibonacci number, or the preceding Fibonacci number. And so we're going to check to see if that number that we're looking for is in our dictionary. If it's in our dictionary, instead of recalculating it, we're just going to use the value in our dictionary, right? Why repeat the work? But if it's not, we're going to have to call a Fibonacci function to get that value and then return it back out. And so notice what I've done here is I actually have 2 values that are being returned from our function. This is valid in Python. It's not valid in other programming languages, but in Python, you can return more than one value out from your function. So if you look at our return statement down here, you can see that we're returning 1 less plus 2 less, and then pass num. And so we're going to save it in these 2 different variables. Now we're going to have to update pass num with the value of 1 less, just so that our dictionary is updated, and when we use it later on, we have that information available. So now with 2 less, we're going to do pretty much the same thing, except the only difference is going to be -2 instead of -1. As you can see, pretty similar to what we did previously. And then finally, we're going to return 1 less plus 2 less, again, to get that Fibonacci number of num. And then we're also going to return the dictionary just to be safe. Now, if I run this, notice if we do it with 10, we still get it lightning fast. Oh, forgot to print it out. Let's go ahead and print it out again. We still get 89 lightning fast. But if we do it with 95, which last time took us forever and ever and ever and have to kill it before it finished, notice that we get it much, much, much faster. And so that's the power of saving this work and not having to repeat it. Okay, so question number 3 was asking us to calculate the values of a hand of cards. And so this is going to be our first program of multiple programs that are going to ultimately build or simulate the card game Yusuf. We're going to define a function that's called handSum. It's going to take in 2 arrays, or 2 lists. The first list is going to be values, and the second list is going to be suits. And so we're seeing this assert function again, and what assert it does is it ensures that some value is true. If it is not true, it will crash the program and it will tell us to stop running. And the reason that assert is used, you might think, well, why would I purposely want to crash my program? And the answer is you'd want to crash your program in a case that you know is not supposed to happen, right? So you'd much rather figure out that something bad is happening earlier on than find out your program's not working for some reason and have to dig through your code to see where exactly the error is. With the assert function, you can say, hey, this has to be true at this point. If it's not true and it throws an error, you know exactly where to look with this. And so we know that we have to have the number of values in our value list and the number of suits in our suit list have to be equal. And if they're not equal, something's going wrong, and we need to, seriously reconsider what input is being passed in. So next I'm going to define a dictionary that's going to hold the values of all of the cards. So face cards are going to be 10, and then an ace is 1. Now notice that I'm also adding the values of the 10 of the number cards in the deck of cards. I'm giving them the value that they're assigned to. And the reason I'm doing that is because this is going to be a string, but the number is going to be an integer. And so we want to make sure that we have a key so that we can look up, what value it is and proceed from there. And so this is just a way of keeping everything in this one dictionary all good to go. So anyway, now we're going to get to the sum. So for the sum, all we're going to do is for each of the values in the list, we're just going to add the value to the sum. Again, looking it up in our dictionary to make sure to see what the actual value is, and then adding it to the sum. Then we'll return it back out to the user. And so as you can see here, I have an example where we have 4 cards, and if we run it, we get 22, which is correct. Let's say I change this, we'll get 23. Let's say I remove a card, but I don't remove the corresponding suit. We're going to get an error. You can see there's an assertion error. So I'll go ahead and remove the corresponding suit. We run it again, and we get the correct answer.